All right, you guys, we're going to continue our discussion on graphing rational functions. All right, so I have a new problem here. It says follow the steps for graphing a rational function to graph the function r of x equals 9 over x squared minus 16. So the directions say, if needed, first write the given function as a single rational expression, then factor the numerator and the denominator of r of x, and then select the correct choice below, and if necessary, fill in the answer box to complete your choice. Okay, so for the first part, we need to put our function in lowest terms. All right, so we have r of x equals 9 over x squared minus 16. So to put that in lowest terms, to put it in factored form, all right, the numerator is completely factored, but the denominator, that's difference of two squares. So that's x minus 4, x plus 4. Okay, so we would choose A for this portion, and we would write this answer. Okay. All right, for the second portion, it says, what is the domain of r of x? Select the correct choice below, and if necessary, fill in the answer box to complete your choice. Okay, so to find the domain, okay, if you're looking for the domain of a rational function, all right, remember that the denominator cannot equal 0, okay? And when you find the values that make it 0, you have to exclude those values, okay? All right, so since we've already factored our function, I'm going to go ahead and set that denominator equal to 0. And I'm going to set each one of those factors equal to 0. And I'm going to solve for x. Okay, so the two values I got was positive 4 and negative 4. So that means that I can plug in any value of x into that function, because remember, when they're asking you for a domain, they're asking you what inputs can you put into your function. So I can plug in anything I want as long as I don't plug in negative 4 or positive 4, because they make the denominator equal 0. Okay, so if I were to write that in set builder notation, I would write brace x such that x cannot equal negative 4 and positive 4. So remember, you always list your values from smallest to greatest. Okay, so if you guys are looking at your assignment, you're going to choose A, and you're going to write this answer that we just put. You're going to put in the negative 4 and the positive 4. Okay. All right, moving right along. All right, the next part says write r of x in lowest terms. Select the correct choice below, and if necessary, fill in the answer box to complete your choice. All right, so to put in lowest terms means that you have completely factored your function and you have no common terms that appear in the numerator and the denominator. So remember, we factored our function up here, okay? So if we are looking at it, there are no common factors that appear in the numerator and the denominator. So our function's already in lowest terms, okay? So we can tell them, nope, we don't have to do anything. We're already in lowest terms, okay? All right, next part. It says locate the intercepts of the graph. Select the correct choice below, and if necessary, fill in the answer box or boxes to complete your choice. All right, so we know that there's two types of intercepts. Let's change our color. All right, we know we have x-intercepts and we have y-intercepts, okay? If we're looking for our x-intercepts first, that means we're going to set y equal to 0 and we're going to solve. So everywhere in our function where we see a y, okay, so remember we're in function notation, so r of x takes the place of y. We're going to replace it with 0. So we're going to have 0 equals 9 over x plus 4, x minus 4. Okay, I can turn this into a proportion and solve. So I'm going to cross multiply. So I'm going to have 0 times the denominator, which is 0, and 1 times 9, which is 9. Okay. Now 0 does not equal 9. Okay. That's a contradiction. It's not true. So that tells me that I have no x-intercepts. Okay. All right, let's try to solve for our y-intercepts. Okay, so if we're looking for y-intercepts, we set x equal to 0. So everywhere in my function where I see an x, I'm going to make it 0. So I'm going to have 9 over 0 minus 4, 0 minus 4. And I'm going to solve. So the numerator stays the same. 9 over 0 plus 4 is 4. 0 minus 4 is negative 4. I'm going to simplify the denominator. So that's 9 over negative 16. So that's my y-intercept. Okay. So I had no x-intercepts and one y-intercept. So let's go back over to our choices. All right, so choice A says that the graph has x-intercepts and y-intercept. Choice B says the graph has a y-intercept and no x-intercept. C says the graph has x-intercepts and no y. And D says the graph has neither x or y-intercepts. So what did we get? We had no x-intercept and one y-intercept. So we're going to choose B, okay? And our y-intercept was negative 9 over 16. So it just says type an integer or a fraction. So we would just write negative 9/16 there, okay? All right, let's move to the next one. All right, the next part says determine the behavior of the graph of R at any x-intercepts. Select the correct choice below, and if necessary, fill in the answer box or boxes to complete your choice. So remember, we had no x-intercepts. We found that up here. So if we don't have any x-intercepts, there can't be any behavior at any x-intercepts. So when we answer that part, we're going to come down here and say, well, there was no x-intercept. So we get to skip that one. All right, let's move to the next one. The next part says determine the vertical asymptote or asymptotes if one exists. Select the correct choice below, and if necessary, fill in the answer box or boxes to complete your choice. All right, let's change our color. All right, so to find vertical asymptotes, okay. Okay, so remember all right, I abbreviate them VAs. So if you guys see me do that. All right, so remember to find vertical asymptotes. You set the denominator equal to 0 and you solve. Okay, so our denominator, if you guys remember, is x minus 4, x plus 4. Okay, so I'm going to set that equal to 0. And I'm going to solve for x, so it's already factored, so I'm going to set each one of those factors equal to 0. All right, so I have two vertical asymptotes, one at x equals negative 4 and the other one at x equals positive 4. So let's see what our choices are. So it says the function has one vertical asymptote, the function has two vertical asymptotes, the function has three vertical asymptotes, there is no vertical asymptote. All right, so we know we're at B because we have 2, and it says the leftmost. Okay, when they say leftmost, you can think about the smallest one, and the rightmost would be the largest one. So make sure you're putting them in the right spot. So our smallest or our leftmost would be at negative 4. And x equals 4 would be the other one. Okay. And I put it as x equals, and x equals, not just the number, because the directions say to type equations. So be careful. Okay. All right, let's move to the next part. So it says determine the behavior of the graph on either side of any vertical asymptotes if one exists. Select the correct choice below, and if necessary, fill in the answer box or boxes to complete your choice. Okay, so when you're looking at the behavior at the asymptotes, okay, remember you're looking at the multiplicity. So Okay, so I want to look at the degree on the factor where each one of those vertical asymptotes came from. Okay, so remember when we wrote our denominator here, okay, I need to look at what the exponents were. So the exponent on each one of these factors is 1. Okay, so the multiplicity is 1. All right, 1 is odd. Okay, and remember when it comes to the behavior at asymptotes, you only have 2 choices. Okay, so either your function is going to clash, remember I called it that, or it's going to clap. Okay, it clashes if the multiplicity is odd, and it claps if the multiplicity is even. Okay, so I called it clashing and clapping, but another way to think about it is that the function approaches different infinities as it approaches that asymptote. Okay, which is why it's clashing. Clapping means that they both approach the same infinity, so whether that's up or down. I meant to draw a dashed line. So something like that, okay? So since our multiplicity is odd, we are clashing at both of our asymptotes, which means we are approaching different infinities. From each side. Okay, which means that as you come from the left side or right side, you might be going to positive infinity on one side and negative infinity on the other side. So let's go and look at our choices. So let's see. A says that it approaches infinity on one side of the asymptote at x equals blank and negative infinity on the other, and then it approaches either positive or negative infinity on both sides. Well, A is not right. B, it approaches infinity on one side of the asymptote and negative infinity on the other. That's what we're looking for. That's clashing. All right, so that's our choice. And it's clashing at both of our asymptotes, not just at one. So we can put at -4 and 4. Okay, cool. All right, let's move to the next one. So the next one says determine the horizontal asymptote if one exists. Select the correct choice below, and if necessary, fill in the answer boxes. All right, let's change our color again. Okay, so if we're looking for horizontal asymptotes, okay, so remember I abbreviate them HAs. All right, so horizontal asymptotes occur. Remember, you have those 2 cases. So case 1 is if the larger degree is in the denominator. Okay, case 2 is if the degrees were the same. Okay, so if we look at our function from above was r of x equals 9 over x squared minus 16. Okay, so if we're looking at the degree in the numerator is 0. There's no variables there. So the degree up here, degree in the top, is 0. The degree in the bottom is 2. Okay, now when you're looking for horizontal asymptotes, the difference in the degrees can only be by 2. Okay, for oblique asymptotes, remember it's a little different. So I believe that this question is going to ask us that. So I'll wait till we get there. All right, so if we're comparing the degrees, the larger degree for this problem is in the denominator. So since the larger degree is in the denominator, yes, we have a horizontal asymptote. Okay. And if the larger degree is in the bottom, automatically your horizontal asymptote is at y equals 0. Okay, so there's no work involved. It's automatically y equals 0. Okay, so let's go to our answer choices. So A says the function has 1 horizontal asymptote, B says the function has 2 horizontal asymptotes, and C says that there's no horizontal asymptote. Well, we just found that there's one, and it's at y equals 0. Okay, so make sure you write an equation because the prompt tells you to write an equation. Okay. All right, moving along. All right, the next part says determine the oblique asymptotes if one exists. Okay, so if we're looking for oblique asymptotes, okay, I abbreviate them OAs. Okay, remember oblique asymptotes happen if your larger degree is in the numerator. Okay, and the difference of your degrees can only be by 1. Okay, so if we're looking at our problem, okay, we automatically know right now we're not going to have an oblique asymptote. And the reason why we know that is because we already had a horizontal. Okay, so remember in my previous videos, I told you guys no hose, which meant that you're not going to have an oblique and a horizontal on the same graph. You're either going to have one or the other or none at all. Okay, so for us, we have no oblique asymptote. So we can say no oblique. All right, let's go to the next one. So it says determine the points, if any, at which the graph of R intersects the horizontal or oblique asymptote. If one exists, select the correct answer choice below. If necessary, fill in the answer box to complete your choice. All right, let's change colors. Okay, so if you want to find out if your graph intersects an asymptote, particularly a horizontal or an oblique, because your graph is never going to cross a vertical asymptote, okay, you need to set your function equal to whatever value you got for that asymptote. So we had a horizontal asymptote at y equals 0. So we're going to set our function, we're going to set r of x equal to our horizontal asymptote, okay? So for us, we're going to say our function was 9 over x squared minus 16. I'll write it in the factor form. X minus 4, x plus 4. We're going to set it equal to 0 because that's what our horizontal asymptote was. Okay. And we're going to solve that. So I can make a proportion, cross multiply. 9 equals 0. That's not true. That's a contradiction. So our graph does not intersect the asymptote. Okay, so we can go up here and tell them. Let's see, what are our answer choices? So the graph of R intersects the horizontal asymptote or oblique? Nope. The graph of R intersects the horizontal or oblique asymptote at infinitely many? Nope. There is no point at which the graph of R intersects the asymptote. Yep, that's us. C. All right, next part says, use the real zeros of the numerator and the denominator of R to divide the x-axis into intervals. Determine where the graph of R is above or below the x-axis by choosing a number in each interval and evaluating R there. Select the correct choice below and fill in the answer box or boxes to complete your choice. Okay, so the real zeros are the same thing as our intercepts, okay? So let's go back, retrace our steps. All right, so remember here, okay, when we were looking for the intercepts, we had no x-intercepts and we only had a y-intercept, okay? So let's go back. It was negative 9 over 16. All right, so let's see what they wanted us to do. The real zeros that divide the x-axis. Okay, so what you're going to do, if you want to find out where your function is increasing or decreasing, you're going to take these critical points into account. So let's change our color. All right, so we're going to divide our x-axis up. So let me slide this over. Okay, so we're going to divide our x-axis. Okay, using the following points. So if you have any x-intercepts, if you have any vertical asymptotes, okay, and if you were to have any holes. So we haven't gotten the holes yet, so don't worry about that right now, okay? So we had no x-intercepts. So we had none. we had two vertical asymptotes. So they were at -4 and +4, and we had no holes. So if I draw a number line, I'm going to place those values on there the way that they would naturally occur. So -4 is smaller, so I'm going to make it over here. And 4 is larger. Okay. Now I need to choose test points because I'm interested to see whether my graph is above or below. So these created intervals. So this interval is from -infinity to -4. The one in the middle is from -4 to 4. And the last one is from 4 to infinity. Okay. So I need to choose test points. It doesn't matter what I choose. I just need to make sure that my test points actually fall in the interval I'm trying to test. So I'm going to choose -5 for this one. I'll choose 1 for this one, and I'll choose 5 for this one, okay? So what we need to do, we're plugging in our test values into our function to see if we get a value that's positive, which means that we would be above the x-axis, or negative. That would tell me I was below the x-axis, okay? So remember our function, in case you forgot, r of x equals 9 x minus 4, x plus 4. Okay, so I'm going to plug those values in. So this one would give me 9 over all right, I would simplify that. 9, that would be -9 and -1. All right, that would give me 9 over 9, which would give me 1. All right, so that's positive, which means in this interval, I'm going to be above the x-axis. Okay, now I'm going to do the exact same test for my other two intervals. All right, so this one, I got a negative number. So because it's negative, I'm below the x-axis. Okay, try the last one. All right, so that would be 9 over 50 and 15, 65. All right, so for this last interval, that's positive, which means that I'm above the x-axis. All right, so knowing that information, let's see if we can go back and answer the question. All right, so it says that the graph of R is above the x-axis on these intervals. All right, so let's go back. We said that it's above from -infinity to -4 and from 4 to +infinity. All right, so we would say it's above there. The graph is below, the graph is above and below. Okay, so we have both. So we're going to choose C. We're going to say where it's above, that was our 2, -infinity to -4, 4 to +infinity. And then where it was below, that was this middle one, which was -4 to 4. Okay, so it says make sure you write your answers in interval notation, which we did, and use a comma to separate your answers as necessary. So for this top one, even though I don't have enough space, you're going to need to separate those by a comma. Okay. All right, let's look at the last part. Use the results from the previous steps of R to choose the correct graph. Okay, so in this previous step, okay, we said that we should be, well, first, let's look at the main things. We already know that we have two vertical asymptotes. So automatically, let's see if I can make these bigger for you guys. There we go, that's better. All right, so we already know we have two vertical asymptotes. So automatically, C is out, and so is A, okay, because they only have one vertical asymptote. The second thing that we know, so both of these, they look like they're in the same spot for both B and D, the vertical asymptotes, all right? And we just said that the graph should be above the x-axis between -infinity and -4 and 4 to +infinity. So above. So here, do you see how this function is below? Let me change the color for you. All right, so on this first graph, the function is below the x-axis on those two intervals that we said. We said that it should be above. It should look like how D is looking. All right, so our right answer for our problem is D. Okay, awesome. I hope this helps.